All right, so our final two parametric equations, okay? So here we have, so again, x is equal to 3 cosine of theta, y is equal to 4 sine of theta, or theta is somewhere between 0 and 2 pi. Now, if we were coming up with a table, okay, again, we don't have a t, this time it's theta instead. We can still plug in values, okay? And so we'll have x is equal to 3 cosine of theta, and then our y, 4 sine of theta, and then finally our point. Now, let's think about this logically. You could pick any point between 0 and 2 pi, right? But let's pick points that when you have on our unit circle, they end up being quadrantal angles, right? They end up being the 1, 0 or the 0, 1. And the reason we want to pick that is because at least one of the numbers will be 0 and one of the numbers will be 1. So the first theta I'm going to pick is 0 radians. So when I plug in the cosine of 0, right, cosine of 0 is 1, so 3 times 1 is 3. But then the sine of 0 is 0, so this will just be 0. So I'll be at the point 3, 0. So that's a lovely number. Okay, after 0, let's pick 90 degrees. It's in radians, so we'll say pi over 2. So 3 cosine pi over 2, so that would be 0. And then if I plug in a 4 of pi over 2, this is 1, so this will be 4. So our point would be 0, 4. So 0, 4, I'm in that direction. And then I'm down to 180, or aka pi. So 3 cosine of pi, so this is -1, so -3. So 4 sine of pi would just be 0. So -3, 0 would be right there. And then let's get down to 270, or aka 3 pi over 2. So 3 cosine of 3 pi over 2 is just 0. And then sine of 3 pi over 2 times 4 is -4. So 0, -4. Bam, right there. But we're going all the way to 2 pi. So let's include 2 pi. So 2 pi is the same as 0, right? So I'm not going to rewrite it down here. I also ran out of room here. So I know that I'll be at 3, 0. So essentially, we have just created something that is going to be connected. Okay, and it's actually an ellipse, even though we didn't talk about ellipses this year. This is an ellipse. And so it just keeps going around in this lovely circle. So we sketched it, we oriented. Now the rectangular equation. Okay, so I want you to be using your trig identity. So I want you to use the identity sine squared of theta plus cosine squared of theta is equal to 1. Okay, so looking at this problem, right, we have, I'm going to rewrite it down here, so x is equal to 3 cosine of theta. I'm going to divide both sides by 3. So how do I make this squared? Well, that's easy. I can just square it, which means I'm going to square it on that side. And then I'll do the same thing for the y. So I'm going to first divide by 4. So y divided by 4 is equal to sine of theta. And again, I'm going to square this side and square this side. So if I do that, I'm going to replace sine squared of theta with y over 4 squared, which essentially will just be y squared over 16. And I'll replace cosine squared of theta with x squared over 9. And I'm going to set that equal to 1. So that's what makes this an ellipse. If we remember an ellipse from, I believe, integrated 3. Okay? Do you have to remember that it's ellipse? No. The great thing about an ellipse when it's set to 0 is that what's the square root of 16? It's 4. So we go, notice it's under the y, so we would go up 4, down 4. Square root of 9 is 3. Notice it's under the x. So notice that you're going to go +3 and -3 in both directions. Not that we have to remember that for ellipses. You can always set up this lovely chart. And that's it. That's all you have to do. So if we can remember this lovely equation, right, your trig identity, coming back to those trig identities, it'll make life a little bit easier. Okay? So why don't you go ahead and pause the video, try this one on your own, and see kind of what happens here. I'm going to again set up a table. This time there is a t in it. But go ahead and pause the video and try this one on your own and see if you get the same graph and same rectangular equation that I am going to get. Right, so coming back from the paused video, so we can see that I'm still writing things down, and I already know that 2 pi is going to be the same as 0. Okay, so cosine of 0 minus 2, so 1 minus 2 is going to give me -1, and then sine of 0 is 0 plus 3, so this will just be 3, so this will be -1, 3. Cosine of pi over 2 minus 2, so 0 minus 2 is -2. Sine of pi over 2 plus 3, so this will be 1. 1 plus 3 is 4, so -2, 4. Cosine of pi minus 2, so -1. -1 minus 2 is -3. Sine of pi is 0. 0 plus 3 is still 3, so -3, 3. Cosine of 3 pi over 2 minus 2, so that should be the same thing as -2. And then sine of 3 pi over 2, and then plus 3, so -1 plus 3 is 2, so -2, 2. So let's go ahead and plot this number. So -1, 3, -2, 4, -3, 3, -2, 2. And then 2, 0 comes right back into here. So we have this lovely, it looks kind of like a circle. So orientation, orientation. Notice that the orientation on this problem, as well as this problem, are going in the same direction as your unit circle, right? So again, fun facts that we can use. So again, how can I use the sine squared of theta plus the cosine squared of theta is equal to 1 equation? So let's come back and remember that it was cosine t minus 2 is equal to x. So I'm going to go ahead and cosine, instead of theta, let's write t. So that way we know what we're doing. So this will become x minus 2. Again, I'm going to square that. I'm going to square that. So I'm going to replace this with an x minus 2 squared. And then my sine of t plus 3 is equal to y. Sine of t is y minus 3. Again, I'm going to square that and then square that. So y minus 3. Ooh, that's supposed to not be cubed. That's supposed to be squared. So squared. And there you go. So technically our center, if we nitpicky, is 2 comma, or sorry, this is supposed to be plus 2 comma, or -2 comma 3, and -2 comma 3 is right here. And again, we go up 1, we go down 1, we go right 1, we go left 1 because the r radius is 1. So again, we can recognize that this is a circle. If you didn't know that it was a circle, no big deal. But we can get at least this far. So that's the biggest thing. Can we make a table? Can we plot some points? Again, pick your quadrantal angles. Don't pick 30 degrees. I mean, you can, but then you just have decimals that you're dealing with instead of integers. And then just remember our sine squared plus cosine squared is always equal to the number 1. So if we can use that identity, it will help us create these parametric equations.